our little formula for anyway, whatever, the arrow's staying there, I guess. This is our exponential equation. If we're going to write an equation, we're going to start with f of x, or y equals a times b to the x. And I kind of talked about this yesterday when we talked about the graphs, but if a is bigger than 0 and b is greater than 1, if your base is bigger than 1, then that's always going to be increasing. So it's going to look like this type of graph when you graph it. And we call that an exponential growth function. Bacteria, I believe they reproduce exponentially, and so over time they're growing more and more. As time goes on, the population is getting bigger and bigger. That's exponential growth. B, I don't know why I capitalized that here, but B is the growth factor. So if they ask you what is the growth factor, it's just whatever the base is. That's by how much it's growing. We also can have exponential decay, and again, pay attention to the if part here. If a is bigger than 0 and b is less than 1, so if b is a fraction, kind of what we're looking at here, then our function is going to be decreasing. It's going to look like it flipped over the y-axis. It's going to kind of look like this, still that shape, but going the opposite way. And we call that an exponential decay function because over time it's getting smaller. Radioactive decay is the one that we use the most. Maybe you've done that in chemistry class, biology class, talk about that. What? Yeah, like the half-life stuff. That means if it's half-life, it's how long it takes for half of it to be gone. And over time, it's getting smaller and smaller and smaller. So part of your homework today is just identifying whether it's exponential growth, exponential decay, and getting that growth or decay factor. But kind of tricky sometimes because they don't always start with b greater than 1, b less than 1. You have to kind of think about that a little bit. So that's where we're going to start. Oh, that's 3 examples. What's wrong with you? The first 2 are really short. The last one's just really short. So this is the first part of your homework today. State whether the function is exponential growth or exponential decay. And maybe it even asks you to state the growth factor or decay factor, but we can do that as well. And if you're not sure, if you don't remember all the rules for it, basically what you want to do is see what's happening as you plug in bigger and bigger numbers for x. Are your answers getting bigger or getting smaller? That's kind of what you're looking for. The thing that we just typed on the last page was talking about a and b. I'm going to go back to adult pages for just a minute. If it's exponential growth, you're looking for a is greater than 1, b is greater than 1. I always look at the exponent, and I feel like that's not really telling us anything right now. What do you think for number 1? Do you think that it's growth or decay? It doesn't really fit what we just wrote over there, though. Do you agree with that? Oh, I know what we could do. Okay, sorry. I know I can make this fit. Could I write this as 1 over 3 to the 2x power? Like, could I say the base is really like 1/3 because it's a negative exponent? That's where that rule comes from. It's all right. You don't have to do it because I always just look at the exponent. Since the exponent is negative, is that what you all thought of and why it's decay? That's what I think of too. But I was just trying to show you where the book rule comes from. Because negative exponent really means flip it over. That means that our base is actually less than 1 because of the negative exponent. That's tricky. What if I had, let me just skip this one for a minute. I'll make that number for you in a minute. What if I said f of x equals 1/3 to the x power? To the negative x power. What does that negative do to 1/3? You could write that as 3 to the x because negative means flip it over. So would this be exponential growth or exponential decay? This would be exponential growth because it was a fraction, but then the negative flipped it over. You see what I'm saying there? It would be 3. Yes, Sarah. B is the base. Look, I'm gonna look and make sure I know. Why do they write it so confusing? What about my 1/e to the x? What do you think about that one? Growth or decay, Caitlin? Are you just guessing? It is a fraction with a positive exponent, which means I think that it's decay. You could write this as e to the negative x if you wanted to. Just think about, like, I always think decay is negative exponents and growth is not negative exponents. But that's not always true because they can trick you with the fraction stuff, right? So this one is exponential decay. I think I'm just overthinking it too much. Yeah. Or e to the negative 1. That would be the same thing. I even wrote on my paper, tricky. I wrote this one was tricky. I don't know, because negative exponent told me decay, but that's not what the definition. I kind of obviously didn't pay attention to what the definition was telling us. Alright, sorry. I feel like I made that way more complicated than it is. So let's just move on. Alright, I'm giving you a few story problems today. We're just going to do one, but we're going to talk about how we can do this. And you can maybe not write all of this stuff, definitely write the function. But this is an equation for the population in Ohio. This is actually called a logistic function, but you know, that's really okay if you don't know that. Here's what's important about these story problems. Make sure you know what everything's representing. P is the population, which means what you get out of here, like your answer that you get, is the population in millions. So if you got an answer of 7, that means 7 million people. And T, that's our other variable in this problem, T is the number of years since 1900. So if you got an answer for T like 72, that means 72 years since 1900, or so kind of think about that when you're reading these problems. So a lot of this today, I don't know if you remember much of this from last year, but we learned how to solve problems like this. How do you solve for T? There's a whole bunch of logarithm stuff you can do. We're kind of taking baby steps back into that. A lot of what we're doing today is just going to be plugging in values and maybe approximating the answer, just getting used to seeing these types of problems again. So part A says, how many people were there in Ohio in 1950? So I want to know, what do we need to do to find how many people were in Ohio in 1950? Plug in 1950 for T? Just 50, because T is the number of years since 1900, so you have to pay attention to that. If you don't have a calculator, I want you to come and get one, because I want to talk about approximating and how to get very precise answers here. The nice thing is that with calculators, most calculators now, you can type in a bunch of stuff at once, but I just want to caution you about approximating your answers. Even though we're going to round at the end, maybe round to like the nearest person, you don't want to round until the very end, because you can have, I don't know, I call it round-off error, because if you round all throughout the problem, your answer gets more and more inaccurate every time you round. So I always say round at the very end, or keep lots of decimals until the very end, because otherwise your answer's not going to match mine, and I'm probably going to mark a half point off if you're rounding incorrectly. So if this were me, I would probably maybe even type the whole bottom in at once, or maybe even the whole thing at once, but I want to show you how I'm going to write lots of stuff here. So I'm going to type the bottom in my calculator, because I can do that all at once. 1 plus 2.402 times E, and my calculator automatically puts E caret parenthesis, so you just have to type what you do in the parenthesis, negative 0.0309 times 50, and close the parenthesis. And I didn't do the top yet, so let's see if we agree on the bottom. I got 1.512375115. No? Third one down, second element. You have lots of this. Your point zero to your point. Here's what I want to say. If you just rounded this to 1.5 and cut off all those other decimals, or let's say you just did this part first and you rounded, and then you multiplied and you rounded, and then you added 1 and you rounded again, the more you round, the more inaccurate your results. So when you're doing these problems and you're using a calculator, round at the end, keep lots of decimals all the way through the problem, and then your answer should match what I have and what the back of the book has. So I'm going to type this in, 12.79 divided by this giant number here. 115. And remember what we're getting here. We're getting the population. And so, I don't know, I might tell you what's around to. But I got like 8.456896621. Did you get that? Try it again. Take this divided by this. 2.1. That's what I got. Do I write that? Do I write 8.32 here? Or whatever, 8.4. 4, 5, 6, 8, 9, 7. That's millions, right? Do you agree with that? It's like 8 million people. So guess what you can do? Instead of writing 8.4568997, I'm just going to put commas here. There are 8,456,897 people. You're right. You could round and say about 8.5 million, but why when we have all these numbers? Let's get exact. So you have to pay attention to what your answer is representing in these problems. How do you feel about that? If you're talking about millions, yes, I could go 7 decimals. Just go to the thousands, yeah. Henry, did you get yours to work? Yeah. When was the population 10 million? Now, this is where, if you remember how to solve these from last year, you might go ahead and jump to solving these. But we're kind of not there yet. We haven't even talked about logarithms yet and how we would solve this. But could you approximate, could you plug in different values? If we know in 1950 there were about 8.5 million, could you pick a few numbers and see when it gets to over 10 million? Yeah, and that's kind of what they expect you to do today. So I just said, well, what about 1960? And I just plugged in 60 here instead of 50. And I kind of rounded on these. I'm going to check my math here. 1960, when I plugged that in, I got 9.29 million. So what do you want to guess now? 1960 was too low. But I did 1969 also. I got 9.95 million. So close. I bet 1970 is going to do it, right? I got 10.02 million. And how did I get these numbers? I plugged them in up here every time. So when was the population 10 million? In 1970. You can also use the graphing calculator for these, and I think that maybe section 3.2, we'll talk about the graphing calculator stuff a little bit more. But since we have a little bit of time, I want to show you how you could do part B with the graphing calculator, and then I'll be done, okay? So if we wanted to see when does this equation equal 10 million, we can graph this equation, and we can graph the equation just y equals 10 million, and we can see where they cross. And the calculator will actually find the exact point where they cross for us. But if you want to go to 10 million, think about you're going to have to change your windows. Let me just kind of show you this, because in the next section, which means Monday, when we return, we're going to talk about how we can use the graphing calculator. I think that's going to come up. Why is this the slowest program ever? Another thing that we're going to talk about on Monday is how to put this in your calculator correctly. There's lots of parentheses usually involved. But I'm going to type in 12.79 divided by, and I want the whole thing in parentheses, so I'm going to do parentheses 1 plus 2.402 times E, and see it automatically puts my little exponent up there, negative 0.0309. And I have to use X because I'm graphing it. It's not going to graph T. Close the parentheses. Okay. And then I'm going to type in 10 million. Oh, should I type in 10 million or should I type in 10? Right? Because the equation, let's go back to the equation for a minute. The equation, P is population in millions. So I was getting answers like 9.29, 9.95, 10. So I'm not going to type in 10 million here. I'm just going to type in 10. Does that make sense? Because the answer you're going to get is 10. So that makes my window much better. And I could go and look at the graph of this, but it's not going to show where they intersect because, look, 10 is way up here, and here's my graph, so that's where I need to look at my window. And let's just start at 0. That would be at 1900. And let's go to 2000, so we could go from 0 to... Let's make that go by tens. And let's let's make the y go from 0 to 100. And let's make that go by tens also. And let's see if we can see if these intersect. Oh, I should have done this. Okay, sorry. I'm going back. I don't need to go to 100 otherwise. Let's make it go to 20. And guess what? Where the population equals 10 is right there. And do you remember that you can find the intersection points if you go to second calc and you want to find where they intersect? You can say, I want this to be my first curve, I want that to be my second curve, and I'm going to guess that they intersect somewhere over here. Somewhere in the year of 1969, they did actually equal 10 million. 1969, and then 6/7 of the way through, so that would be like, what, 2/3 of the way through, and you could actually kind of get the exact answer there. So that's how you can do it with the graphing calculator. I think it's okay today that we can just kind of guess, and then on Monday, I'm going to let you do a few with the graphing calculator, so you're not just randomly guessing nothing answer is. So that's, again, one good use of graphing calculators, instead of us just randomly guessing. Sorry, that's a little bit of time. Here's your homework. We haven't talked about limits, so if it ever says anything about the limits, you don't have to look at it. Are we going to learn about limits? In calculus, we're going to learn about limits, but we're not going to learn about limits in precalculus. That's what we start about. In calculus, once we do a little bit of review of precalculus, the first chapter in calculus is all about limits.